Hello mechanics, and welcome back to some more Scrap Mechanics Science. Last time, we took a look at how to make anything in the game float using these number logic thrusters, and this magical number, using the creation's mass, we calculate the thrust force needed to make it hover like anti-gravity. So it doesn't actually matter how heavy your creation is, and it doesn't matter even if your creation changes mass during gameplay, the thruster force will automatically update using this magic number. So in the last video, I actually showed you guys how to calculate this number using some pretty outdated scientific methods, but it does explain why the number is 3.818. Today, I'm going to be showing you guys another method to calculate the exact same number, but to many much more significant digits. We're going to be super precise because we're using a programmer's method to actually calculate this number using number logic. But before we get into that, there were a few questions on the last video. Like this one asking about the thruster force and if you wanted to use multiple thrusters. So if you remember how to make anything float, it's super simple. You take the creation's mass divided by 3.818. So you gotta remember the mass is on top, 3.818 is on bottom. This is gonna be the thruster force for the entire creation, no matter what the creation is. So if we go ahead and detach this, you're just gonna see, to get this thing to be floating like anti-gravity, like completely like anti-gravity, it's floating like it's in outer space. Now, one of the questions was, what if you have multiple thrusters? What do you do then? So we have multiple thrusters here. We're gonna put 4. So the best way to look at this little bit of logic here is to see this thrust output as the entire creation's mass ready to go. All right, it's ready to go for the entire creation, but this is just one thruster. So what you gotta do is you take this thruster force and divide it by the number of thrusters that you have, in which case I have 4. So entire thruster force divided by 4, this is ready to go for 4 thrusters. And you can see, just like before, this thing is hovering like anti-gravity. Except this time we're using 4 thrusters instead of just 1. Now I actually think that this is a great question to ask. You gotta consider that even if we add weights to this thing, relatively speaking, the thruster force is automatically adjusted, this thing is gonna stay floating. Right? Even if we take off weights, the thing is still gonna stay floating, just like it's anti-gravity. So you really gotta keep in mind that the thruster force that we're calculating here is relative to the entire creation. No matter how heavy it is, we're doing a negative force of gravity here. So this is actually super useful for a lot of things. Let me go ahead and show you one very simple example here. Remember that we have 4 thrusters canceling the force of gravity, so if we go ahead and put 2 thrusters, actually let's keep the corners connected. There you go. So if we have 2 thrusters connected instead of 4, but we're still dividing the force by 4, then technically we created a creation that experiences half gravity. It still falls down, but it's not quite the same thing as something that has normal gravity. And that's because, again, you gotta consider, relative to the anti-gravity force that we calculated, we're only pushing up with half of it. So canceling half of gravity leaves the other half of gravity to do its work. So that's something that you want to keep in mind, is that this thruster force calculated applies to the entire creation like as if it's anti-gravity, and then you can use that information very easily, like if you want to cut gravity in half, but there are other things that you can do with that too. Let me go ahead and show you. Over here, we have the exact same hover thing. This is supposed to be anti-gravity, except this time, we're not actually dividing the thruster force. Instead, we put 2 gimbal thrusters, but we're using the full force. So this actually means, just like before, how we cut gravity in half, this time, we're doubling gravity. So when I turn this on, we're actually going to be accelerating upwards at the same speed that gravity pulls down. This is full-on anti-gravity right here. Check this out. And just before I do that, I set an altitude where the thing turns off. So you can see it doesn't go all the way up to the skybox, like that one over there. Anyway, we go ahead and turn it on, and you can see it shoots up at the speed of gravity, but then falls back down at the speed of gravity, turns back on, goes up at the speed of gravity, falls back down at the speed of gravity, and this is just the creation fluctuating above and below that altitude that I set with number logic. But you can see here very easily that 2 thrusters, without dividing the thruster force, is doubling that anti-gravity force. So if I put 3 thrusters, it would go up at 3 times anti-gravity. If I put 4 thrusters, it would go 4 times anti-gravity. Now you might be sitting there and wondering, like, okay, how is this useful for anyone, or any build, or anything, or gameplay? Like, how is this ever gonna be useful? And you gotta keep in mind that this is just an example to show you how the thrust actually works and what you wanna do to make sure it doesn't fly away. But you can actually expand on that a little bit. Here I have the exact same thing, set to the exact same altitude, but a little bit of extra logic to have a little bit of a buffer area. So check this out, check this out. This is going to be significantly better. Significantly better. Those number blocks on the bottom are for me to check if it's actually hovering around 60 blocks was the altitude that I set. So you can see we're going above and below 60 blocks with like a buffer of 2 blocks. So that's one thing to keep in mind, is that a lot of what I'm showing you guys today is really, it depends on you how you're going to make it useful for yourself. You got to remember that this stuff was just for anti-gravity, but then this stuff over here that I'm showing you guys, we're doing double the force of anti-gravity to actually push ourselves up, and then turning off completely to allow gravity to pull ourselves back down. Hover systems like this depend on what you're designing, and hover systems like, where is it? Where'd it go? Why is it up there? Ah! So hover systems like that, you definitely want to have a thruster to be able to push you up, down, left, right, forward, back. So that is sort of like a different control system, but it really depends on what you want to build. There's also something else very important that you want to keep in mind, especially when building hover systems, is that you can see that I always have 2 thrusters, and they're generally on top, and I put them on the corners so that this thing is balanced. I was a little bit curious, what happens if you build the exact same thing, but it's imbalanced? You actually have thrusters on one side. It should still work, right? It should still work just fine. So let's go ahead and try it. And it hovers at the altitude just fine. There's nothing wrong with this, right? Although you can see, because I built it imbalanced, it's a little bit chaotic. Oh my gosh. Oh my gosh. It's going. It's going. It's this is perpetual. What the frick? I mean, technically, it's like it's hovering at the same altitude, right? Like, you look at those platforms; they're hovering at the same altitude. Well, that's strange. The lift image shows the animation of the gimbal thrusters going crazy up there. Yep, they're spinning. I'm actually a little bit fascinated by this because, I mean, I intended to build something imbalanced, but it's actually really stable, spinning in the air. How did I create something spinning stable? What? Now, one other question that some people had was the precision of the number calculated, 3.818. Where did this number 3.818 even come from? Like, as far as I know, it's an arbitrary thing that has to do with the physics engine that Scrap Mechanic uses. So whatever the default thruster force of 1 is relative to the gravity value set in the physics engine. That's really all it is, just the ratio between those two numbers. But 3.818 is not that precise. I mean, it's actually precise enough for Scrap Mechanic gameplay. You, as a player playing the game, are barely gonna notice that this number is imprecise. Let me actually just go ahead and show you what I mean. So if you actually walk up like super close to the thing, and I have anti-aliasing turned off, you can see that all of the pixels on the screen are moving. This platform, very slowly, is moving upwards. The number 3.818 is actually not correct. There's actually more digits after that 8, and we don't know what they are because we didn't actually measure that precision. So this movement upwards that you're seeing is those missing digits. This is the level of precision that we calculated the number with. And this is what I mean when I say that it really depends on what you're doing, what you're building. Most players in Scrap Mechanic are never going to notice this very subtle difference in thruster force. It's literally going to take like hours for this thing to go upwards and for me to lose track of it in the sky. Now, I was a little bit curious when people were asking where did this number come from, like why is it what it is? So I went ahead and I spent the time searching for a ratio between 2 integers that would equal exactly the number. And I think it's actually really interesting what I found over here. If you see here, I'm actually taking the number 42, which is the answer to everything in the universe, and I'm dividing it by the number of dimensions according to, what is it, M theory? 11-dimensional theory, right? 42 divided by 11 equals exactly 3.81 repeating. 3.818181818181, and so on. That's the closest that I actually got to using 2 whole numbers. 42 divided by 11 equals exactly the ratio that I said earlier. And the thing is, this is actually more precise. This is more precise than what we calculated in the previous video, and that bugs me so much. That bugs me so much. But it's more precise just because we actually have more digit places here. But if we go super close, you're gonna see the exact same thing. This platform is also very slowly going upwards. So we still have the answer to our question. This is not the correct number. This is still not precise enough. Even though we got a little bit closer to the true value, this is still not really precise. But you can see that it's gonna take like thousands of years for, this to be out of my reach. Like I can still grab this on a lift. Even, half an hour later, I'd still be able to reach it with my lift. It's not going anywhere for a long time. I mean, unless you do something really silly, like accidentally push it upwards. Well, it doesn't even go that far, you know what I mean? You'll be fine. So over here, I actually went out of my way to design a programmer's method to calculating the number. So in the last video, we calculated this number by collecting several data points, and we would change the mass of our creation to see what the thrust value is, such that it canceled out the mass. Today, we're going to be doing a different method, where we're actually going to be changing the thrust value for the same mass. This creation is never going to be changing mass, but we are going to be changing thrust value until we get more and more precise digits to calculate the exact value that it needs. So if we go to this creation super close, again with the anti-aliasing, you're going to see this creation is not moving at all. Like, literally not moving at all. Those pixels are not moving. It's going to take millions of years for this creation to go out of your reach or something. Like, you're not going to lose this thing. This is not going to be floating away. This is anti-gravity right here. We might be going a little bit overboard here, because remember, 3.818 is good enough for scrap mechanic gameplay. Human people are rarely going to see that this is not good enough. But 7-digit places, holy moly, it's gonna take millions of years. Like, we're never gonna know it. It's so precise. Like, this is what you want for a flying carpet. Alright, so let's go ahead and get started. Talk about what I actually did here for this logic test. This is gonna be the boring logic part for you guys that aren't into that sort of thing. So we're starting off with the same logic as over there. We're trying to calculate anti-gravity here, but instead this time around, we're starting with a value of 3, which is definitely not good enough. You gotta remember, we're taking the creation's mass divided by 3. All of a sudden, it's a larger thrust value than over there. Because you gotta remember the bottom number of the division. The higher the bottom number is, the lower the value actually is. So we're starting with 3, resulting in higher thrust value. This thing's gonna shoot upwards. Now over here, I actually have a velocity meter. This thing is gonna be measuring if the platform is moving up or down. And it's just gonna tell us over here, are we moving up or are we moving down? That's it. Over here, I actually have a little ticker. Every 10 ticks or so, it's just gonna go tick, 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 tick. That's all that it does. That's really all that it does. And over here, all of this is a digit selector. So all we do, you can see right here, we have this one highlighted, but if we go here, 2, 3, 4, 5, 6, we can select which digit we're gonna be editing. With all of these tick buttons over here, you can see they adjust the counter value over there for different decimal places. So that's how this works. We're gonna be starting with our first significant digit before moving on to the next one. So I think you guys might be able to see how this works. Every so often, we're gonna be tick, 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 tick. So every time the logic ticks, we're gonna be checking which digit place we're on, and we're also gonna be checking if we're moving up or down. Depending on which direction we're moving, we're gonna adjust that digit place up or down. So it's either gonna be a larger or smaller number. So how we actually go about calculating every single digit place is this bit over here, right here. This bit is a counter. It counts 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Every time we flop back and forth between going up and going down, going up and going down, going up and going down, 3 times over, it's going to click the ticker. All right, we have to go up, down, up, down, up, down 3 times for this thing to tick, and we move over to the next significant digit. And this is how I'm taking into account some scrap mechanic physics, because we can calculate what this digit is supposed to be 3 times before being certain and before moving over to the next digit, and then calculate that a full 3 times before being certain and moving over to the next digit. So let's just go ahead and turn this thing on and show you guys what it's all about. We're starting on the first digit over there. We're starting with a value of 3. And let's go ahead and turn this thing on. You're gonna see we're gonna be moving up, and that value is already gonna be adjusted every time this thing ticks. Let's do this. Already going for 4, 3, 4, 5, 4, 3, and we moved over the next significant digit, and now we're calculating between 7 and 9 but then we're going to move over again after 3 times of going up and down. See? It's actually okay if the digit that we're working on is actually higher than it needs to be. You're going to see that, I think, with these digits over here. The digit will probably stop on the number 2 before moving over to the next digit, but that's okay because we're going to be subtracting from the 3rd digit to actually reach 8.818, right? And you're going to see right now, like, the thing looks perfectly stable in my eyes. Like, as a player, I already don't notice 3.81, 3.82, I already don't notice the difference. But you can see we're calculating 3.818 and already moving over to the next significant digit. This is so much better than the old scientific method, being able to use technology and computers to program your solution for you. Like this thing, it doesn't matter how many times I run this, it's gonna calculate the exact same number every time. It's great, it's great. To be able to tell a computer instructions to be able to do work for you. Like, I'm not doing this work, the computer is doing this work. I think it's 7-7. Yeah, just like that. So as you can see, we were able to calculate 3.8186377. And the thing is, this setup here, this programming setup, is only limited by the number of digits that we're able to calculate. As a matter of fact, if we were able to put digit, decimal place, like as many as the computer can handle, we can calculate even more and more, super precise. To the point where it would take eons for us to see this creation moving up or down. This, as a matter of fact, I think it would actually break scrap mechanic physics if it was that stable. This machine is going to calculate the exact same number every single time. Come on, give me the 7-7. The 7-7. 377. You can see that I actually have this tick rate going a little bit faster too, but it should still come out with the same number. There's the 7-7, there's the 7-7. Anyway, so that's why I wanted to show you guys today, is that the number logic stuff, especially if you know how to program, especially if you give it a little bit of thought, and the task that you need to complete, you can design a logical system to do all the work for you. You don't need to do all that human reaction time stuff that we did in the last video. And we get a much better answer, thanks to computers and technology. Man, oh man, I was praising Isaac Newton in the last video, but that guy knew nothing about programming. Nothing about him. Guy's a chump. One last bonus thing for today was, you know, you see these hover systems over here, and this one kind of looks like it's, you know, floating in water almost, right? So I thought that was pretty cool, and if you've seen a previous video of mine, I have this thing, which is a land boat. It uses such heavy blocks that it actually sinks into the ground, and we're a boat that boats on soil, right? But you can see I added some gimbal thrusters up there and a little bit of logic. So I was a little bit curious if I can make this thing float like anti-gravity and make it look like it's floating in water, but in the air, right? So we can choose between being a land boat or an air boat. Not anything but the water, anything but the water. Anyway, let's just go ahead and show you how that went. Yeah. Yeah. I mean, like, oh my gosh. It's really bad, right? Like, holy moly. The thing is though, it's hovering at the set altitude. Like, I set this altitude, which is a little bit higher than those other ones there, but it's doing a perfect job of hovering where it's supposed to be. And I'm actually really surprised at that. The spinning, I have no idea. I think it's just because this land boat uses the ridiculously heavy blocks, like so dense that it sinks underground. So thruster force, trying to deal with that, I think that's what's happening here. It's resulting in this weird spin. You know, oh my god, what's happening to my graphics? What the heck? Did anyone see that? What the heck? There's something very weird. Oh my god, that's weird to look at. Right now we're in free cam. Now we're in follow cam. I don't know what we're following, but we're following. And this is strict follow cam. Free camera, follow cam, strict follow cam. There's literally no difference between any of the cameras. When you're spinning so fast, you actually break follow cam. I mean, we can turn it off and go back down. There you go. No, don't sink down. Don't sink down. There you go. There you go. It's so ridiculous. Anyway, I thought a lot of this hover stuff was pretty cool. Hopefully I expanded your knowledge a little bit, although you just gotta keep in mind what you're building and how you're building it. And of course, there is the more precise number just in case anybody needs it for anything. Oh, I'll also put this on the workshop. So I'm actually going to be putting this up on the workshop for you guys to play with if you ever need the more precise number. I mean, I think I showed it on screen. I think it's 3.8186377. Or if you don't care that much, you can just do 42 divided by 11. It's the same number, pretty much. But for those people that are into programming and designing solutions to their problems, you might be interested in this thing, so... But that's all that I really got to show you guys for today. Hopefully you guys learned something new. Be sure to hit that like button if you like videos like this and you want to see more like it. But also let me know down in the comments below, what do you think? And if there's anything else, any other questions that you have that you want answered, you might just see it in the next video. Thanks for watching, and I'll see you guys next time.